So a dynamical system is a system that doesn't have like a simple causal relationship because it has feedback loops.
Mm-hmm.
So if I pick up this mug and I move it, why did it move? I caused it to move,
Mm-hmm.
right? But what causes a tree to grow?
Mm.
It's not so easy, right? Because
Yeah,
it's like the tree
the
grows
tree.
the leaves capture the sun feeds the tree, which allows it to grow the leaves, right?
Yeah.
Which comes first, the chicken or the egg, the acorn or the oak tree, right? Like you have
The
these
egg.
feedback loops and
I
it
got
gets
an
much more
answer for
complex.
that. It's the egg. Yeah, never
That's
mind. I put that aside.
yeah.
I got a rant on it.
I yeah. Phylogenetically, it's the egg, but trying to answer the question at the phylogenetic
Yeah,
level shows that you misframed the question.
yeah.
But
Fair
but,
enough.
but okay, so when you learn, um, you're engaging in these feedback loops, right? And you have an inherent drive and capacity to learn. So if we treat it as a linear process, it doesn't really work. There's all sorts of points at which treating we tend to treat movement as if people were machines and they're not, and this tends to fail. And so it's one example of the development and kind of understanding of dynamical systems comes through motor learning, and specifically the work of Nikolai Bernstein.
Mm.
So Bernstein discovered that if you look at an experienced blacksmith, the path that the hammer takes to the thing they're hitting is highly variable on every cycle.
Mm.
And in fact, you can sometimes see more variability in the path to the effect. So there's more jargon here, but they talk about effectors and effects. The effector is the thing that makes the thing happen, right? And the effect is what we're trying to have happen. So if the effect that you want is to shoot a basketball, right? You
Mm.
want or the basketball to go through the hoop. You want that thing to be
Oh,
consistent.
I see.
Make that thing consistent by making everything that led up to it consistent. It turns out that's not how we actually work.
Mm.
If you're building a machine, you want those tolerances to be as tight as possible. But we actually have this element of dynamics where you're trying to attune all these variable things that are coming together to create the output. So if you look at Steph Curry, who's the best three-point shooter
Yeah.
in history, he actually has more diversity of muscle activation patterns to achieve his shot than anybody else.
Yeah.
And once you understand,
It's not a machine. It's not a robot. It's
it's not a
different
machine
every
at
time.
all.
It's every time sensitive to the situation he's in.
Yeah, and Bernstein lays out why this has to be the case in this. He lays out two fundamental problems. One is the degrees of freedom problem, and the other is the condition. I'm blanking on the word, but context conditioned variability. So if Steph shot like a robot, where it was exactly the same every time, he would miss almost every time because the context will be different every time.
Mm.
Is his body moving forwards? Is it moving backwards? Is it moving side to side? Is it rotating? Did he get bumped in the air? How tired are his legs?
Mm.
Right? Is it the third quarter? Is it the fourth quarter? Did he just sprint up the court? Did he just have a defensive play? Right? All those things are variable. So he actually has to utilize this motor abundance, this capacity of his body to have lots of different solutions to reach the same effect. It's the same thing with the blacksmith. So what we find is that there's in motor learning, when they talk about positive and negative variation. So there's variation that takes you away from the solution. So if you're shooting a basketball or doing a precision jump, everything that doesn't result in you controlling the precision jump or the basketball good, that's negative variation. So novices will be higher in negative variation
Mm.
than
Mm.
elites. But there's also variation that actually stabilizes the performance. So the classic example that I think is a really nice illustration of that is imagine you take two fingers and you're pushing a bar down. And you're supposed to push it down with, let's say, 10 newtons of force, right? So one solution to that is that both fingers are pushing down with 5 newtons of force, right?
Mm.
If we were to tell you that is the correct solution, you should always be doing that solution. What we would actually be doing is preventing you from being able to use 4 and 6 and 3 and 7 and 2 and 8 and 1 and 9, which are all positive variation.
Mm.
And because the reality is that sometimes one of your fingers is going to like something weird's going to happen, and all of a sudden it's going to be at a 4. You want to be able to adjust for that with the 6. That's the fluctuation. So you have fluctuation around your motor solution. So the way that we coach a lot is over cueing, and actually we end up trying to get rid of the fluctuators that are actually important for stabilizing the performance.
Wow.
So then the way that we coach with Evolve Move Play is very heavily influenced by what's called the constraint-led approach. So rather than saying this is the right way to do a Kong ball, we're going to teach you exactly how to do it. And we're going to be like, okay, your hip is supposed to be here. You need this angle of your shin. You know, you need to be, your whole body needs to be below the height of the object you're going over at some point. We think it's very likely that as coaches, we're going to misidentify some of those elements, or that they're going to be variable from athlete to athlete. Like, what is the optimal width between the front foot and the back foot on a Kong ball?
Yeah, it depends on your skeleton probably a little bit, right?
Yeah, is that
and your
is
height
that,
and everything, the height of the wall, the thickness, everything, the texture, all of it, all the variables come into
exactly
play.
like
So,
are you on sand? Are you
yeah.
on hard turf? Are you on a gymnastics floor? Do you have broad shoulders and narrow hips? Do you have narrow shoulders and broad hips? Do you have long legs proportionally? Do you have short legs proportionally? We're like, you should always be exactly 2 of your feet between your feet when you do your takeoff. We're actually going to limit the athlete's ability to be adaptive. So instead of that, we try to introduce a circumstance in which the athlete can find a solution that is broadly the type of solution that we're looking for. So a really simple constraint that we've used is have an athlete. So one of the things that you'll see is that a lot of athletes will try to do a punch takeoff, right? So in motor learning theory, we talk about this idea of local optimums, right? So you can adopt a strategy that's not the optimal strategy, but that's sufficiently good in a specific circumstance. So you'll see this a lot.
Or would you say also that it is the optimal strategy in even rarer circumstances? But
it might, yeah. There's lots of circumstances where you want to do a punch takeoff. It's just not optimal for the broadest variety of.
Sorry
of
to
things.
nitpick, but I just wanted to clear it
Yeah,
up.
but the thing is that I think for the most part, it is actually optimal on a gymnastics floor. Right? You can utilize the bounce of the springs on a gymnastics floor better by punching hard off of it with both legs than by separating your legs. So lots of athletes learn their vaults first in gymnastics centers, or especially when I was coming up back in the day, right? And so you're going to adopt that local optimum, but then it's actually hard to get out of it. It destabilizes your performance to go and try to find that split takeoff. So I know guys who are very competent athletes who never learned to do a split foot just because they always got worse whenever they tried to, right? But so instead of like taking them through a ton of different drills, a simple way to do it is like have them step back a certain distance from it and say, okay, and make it a little bit of a stretch to get to the vault, and just say, whichever foot they're going to have back, that foot can't go past a certain point, and put a little marker on the ground. And then they'll find that they're going to be able to solve the problem better by sliding that other foot forward. And then they're going to learn to take off with their feet separated. So that's the example of how we can use a constraint to help them organize a solution. And then they're able to find the variation within that solution that works for them.